It's my great pleasure to welcome our next speaker, Terence Tao, from the University of Los Angeles. He is a Fields Medalist. He is a popularizer of all kinds of mathematics to all kinds of audiences. And in the last few years, he's taken an interest in the interaction of technology and mathematics. And the project he'll be telling us about shows the interaction of many such technologies, the interaction of formalization, of AI, both the good old-fashioned kind, and I think to some extent the new kind. He's also been, I think, a real proponent of the idea that one thing that formalization can bring us is huge projects with many collaborators, and so it's not surprising to see 26 names, if I count correctly on that slide. We're looking forward to hearing what you have to say, Terry. Okay,
well, thank you very much, Heather. I'm really sorry I couldn't be there in person. I was really looking forward to meeting, interacting with all of you. And but I did catch up with many of the talks yesterday, at least. Yeah, so I'll be talking about sort of a different way to do mathematics, focusing more on breadth rather than depth, and in particular, large-scale collaborations assisted by modern technology, which is very different from the way we normally do mathematics. So I think compared to other disciplines, we are extremely traditional and slow-moving. I mean, some things do change in our subject, like we have LaTeX now and the archive and so forth, but in many ways, the way we do mathematics hasn't changed in centuries. This image here is a monograph by Cauchy from exactly 200 years ago, 1825, where he introduces what we now call the Cauchy integral formula. And this book is in French and it's not in LaTeX, but it looks almost identical to a book that we would give our graduate students today. And another way in which mathematics has not really changed is how we collaborate or how we don't collaborate. We have slowly increased in our co-authors over time from like 1 to 3, maybe on average. But compared to the other sciences, we are way behind in large-scale collaborations. For various good reasons. Math has a high barrier to entry. It's hard to collaborate with members of the general public. We have this very high standard of proof. We need all our contributions of the paper to be 100% correct, which also makes it hard to collaborate with large numbers of people. And we haven't figured out how to scale our workflows to these large numbers until very recently. So yeah, so the theme of my talk is that because of all the new technologies we have, the new collaboration platforms, new proof verification tools, and experiments in AI, we can now actually do large-scale mathematics. The analogy I like to use is that if math was a social science, then until recently, we've only been doing case studies. Like we've been studying individual theorems, individual objects of but we haven't done population surveys where we study hundreds or thousands of problems at the same time. In a similar dimension, we can also involve much broader people, members of the public now than before. You don't need to understand every single mathematical detail of an entire project in order to contribute to one little part of it, because of our ability to modularize a very complicated project. And we're beginning to use big data, and we're beginning to use open source and really make not just our final proofs available, but also the process to arrive at them, which I think will also be very valuable, especially as we start training AI to also do mathematics. So as we've heard about already yesterday, the one place where this sort of change, this new type of doing mathematics is already more or less established now is in formalization projects. And we now have sort of a standard recipe for doing large-scale formalization. So you saw it in Kevin's talk yesterday. So we create a repository, usually on GitHub, to host the proofs, which are in some languages such as Lean. We also create a blueprint, which is intermediate between an informal proof that already exists and the formal proof that we want to create. But we first have to create this intermediate blueprint where we break up a very complicated theorem into lots and lots of little pieces. which are as independent of each other as possible, so that different people can prove each piece independently of each other, or almost independently of each other. Um, you still need some coordination. You need to have some direction as to who proves what and who claims what. And so you need some sort of chat forum to do that. We can also use the GitHub's various features such as issue tracking to assign tasks, and also sometimes to make changes to things like the blueprint in case some technical issues arise. Um, and we allow contributions from the public. I mean, you can have a closed formalization project, but these projects are very amenable to being completely open, to have pull requests coming from anyone with a GitHub account, basically. And because we have the automatic verification, the continuous integration tools within the GitHub repository, we can be assured that all the contributions that actually pass the CI are actually correct Lean statements. And there are many, many such examples of that now. The PFR project up here was one I actually spoke about in this exact same room almost a year ago. And we saw Kevin's talk yesterday, and Florian will talk right after me about another one of these projects. It's not really the focus of my talk, but I wanted to have record some observations that I found in the formalization projects that I've been involved in. It's really important to have this intermediate blueprint. You can't just sort of jump straight from the informal proof to the formal proof in one go. You have to have this intermediate sketching step, if you wish to, as was discussed yesterday. Because of all this, as Emily said yesterday, because of all this invisible mathematics that needs to be spelled out, you have to be very pedantic. You have to describe the obvious statements, and you have to make things really modular and self-contained. Each step, I mean, not exactly self-contained, but you need to specify exactly what depends on what in a very explicit way. It's also important to make definitions. If a definition is used everywhere throughout the project, you have to fix it fairly early on in the project. Otherwise, it will be very difficult to coordinate the proofs of all dilemmas that rely on that definition. It's not as one advantage that formalization projects have over informal ones. So usually they are more painful to work with than an informal proof. But one place where they are better actually is if you ever need to refactor, like there's a definition and halfway through you decide that you need to switch to a better definition. It's actually much easier to do that in a formal project than it is in an informal one. You refactor informal proof, you create all kinds of inconsistencies and mistakes. But in a formal one, it's actually almost pleasant. Well, in comparison. Another thing which I found, which actually, and Heather, by the way, has a very nice article on this, is that the way you write a proof to make it easy to formalize is actually different from the way you would write a proof which would make it easy for a human to read. So there are many examples of this. So in analysis, which is my field, so when we write an estimates and analysis, we usually hide the constants, and we just say there exists a constant such that this is true, because we don't want to take the time to actually work out the constants. And if you make one error, it cascades, and it's just safer to not write any constants at all. But actually, when you do things formally, it's actually easier to work with explicit constants. There's fewer quantifiers. The tactics are easier to manipulate, and you have this guarantee of correctness. And if you do need to tweak one constant, it's very easy to propagate downstream and fix all the other constants. So it's actually much easier to work with explicit constant estimates. I think you'll see Florian talk about this after me. Another thing is that humans tend to prefer proofs that are written in a very linear fashion. A implies B implies C, or maybe a chain of inequalities. A is less than B is less than C. But actually, if you want to prove things by computer, actually it's often more convenient to just dump into Lean all this inequalities that are somehow somewhat relevant, and then just call a tactic that will find the right way to combine them all together. For example, linear arithmetic, if it's in the case of inequalities. And it took some adjusting to realize that this is actually the smarter thing to do than to just so painfully chain together 10 inequalities into a coherent chain. I do like the fact that formalization is teaching us new ways to describe proofs. And then to riff off what Emily said yesterday, it's often the really obvious statements that are the big stumbling blocks. So for the PFR project, I had the honor of filling in the final sorry for the main theorem. The theorem that I was trying to prove was the following: that if you had 4 independent random variables, x1, x2, x3, and x4, if you grouped 2 of them together, like you had x1, x2, and then the pair x3, x4, if the original 4 random variables were independent, then these 3 new random variables, x1, x2, and the pair x3, x4, were also independent. This is a completely obvious statement. I thought the difficulty would be that I had to do some measure theory. I have to construct product measures and use the pi sigma lemma or something. So I formalized this. The measure theory was actually very straightforward. Mathlib has actually pretty good support for measure theory and product measures and all that. The one step that actually held me up for several hours was proving that the sets 1, 2, and 3,4 were pairwise disjoint. Fortunately, I had help. I mean, I posted on the lean Zulip for the PFR that I couldn't do this one lemma. That if I unfolded all the definitions, I had to check like 20 different that were extremely tedious. But Johan Kammerlin actually, within half an hour, just gave a 5-line proof of this. But it's almost just to decide, but not quite. This was a surprise to me that it was the obvious things that were often the hardest to formalize. Okay, but what this talk is about is not about formalizing existing mathematics, but whether you can use the same paradigms for master collaboration to actually prove new theorems. We don't have that many examples of that so far. Unless you count sort of massive distributed computations, such as searching for Mersenne primes or something. So, I really want actual theorems, not just computations. So I really actually only have 2 examples. One is the Busy Beaver challenge, which was successfully found the 5th Busy Beaver number, which is the length of the longest Turing machine of length 5 with the longest finite holding time. That was worked out just last year, initially as an informal project, but through a bunch of very heroic efforts, the entire project, which had to scan millions of different Turing machines, was formalized in Koch. And then the project I'll be talking about, the Equational Theories project, which was envisioned from the start to be a formal project using Lean. Okay, so what is the Equational Theories project, ETP? So it started about 2 years ago with a Math Overflow question. So someone on Math Overflow asked the following question: is there an identity which lies between the commutative identity and the constant identity? So the commutative identity, you all know, if you take an operation plus, you say it's commutative if x plus y is always equal to y plus x. You say it's constant if all the sums are the same. So if x plus y is equal to z plus w for all x, y, z, w. So of course, that makes the operation very trivial. And of course, the constant identity implies the commutative identity, because the commutative identity says that 2 specific types of sums are equal, and the constant identity says that all sums are equal. But this person asked, is there a third identity which is strictly in logical strength, between the constant identity and the commutative identity? So this was a question, and in 3 hours, it was answered by somebody else. So somebody else just said, okay, here's an identity, and here's a 10-line proof that it is strictly between the constant identity and the commutative identity. Okay, so this was a very typical Math Overflow interaction. The next day, the person who asked the previous question asked a very similar question: is the identity between the associative identity and the constant identity? And this one turned out to be a bit trickier. So what happened was that Pace Nielsen narrowed down the possible candidates. He said that so he has some nice arguments that show that there were only a certain finite number of possible identities that could lie between these two identities. And then I was able to study one of them. And it turns out that this particular identity lies in between those the constant law and the associative law. And then I started playing around with this. And so I actually took a few more identities and I started by hand figuring out how they implied each other. And so combining the previous results with a couple more by hand formalizations, I think I took about 10 identities and I worked out all the implications between them. And then I thought this might be a fun thing to extend. So I commented on that post. It might be a suitable undergraduate project to extend this diagram to cover other short identities for magmas. A magma is just a set of a single binary operation. And then, as an afterthought, it might be a suitable graduate research project to find a way to do this automatically using proof assistance and possibly machine learning or AI tools. So I thought this was something that someone might be interested in. I posted on my social media the next day a specific concrete project to take all the laws which were as complicated as the associative law, so involving at least at most four operations. And so I guessed that there were about 1,000 of such laws. Turns out there's 4,000. And then the challenge was just to work out all the possible implications between them and to see whether the current automated tools are capable enough of doing this. But some people said, yeah, this sounds cool, but no one actually went ahead and did it. I think that everyone was waiting for somebody else to take the lead. So a year passed, nothing happened. But in the meantime, I got interested in Lean, and I formalized. I ran a couple of formalization projects, in particular this PFR project. But I was interested in using these platforms to actually prove some new theorems. And so I was looking for a good pilot project for this. And I kind of knew what I was looking for. I wanted because it was kind of similar to the polymath projects that I was involved in many years ago. I wanted a project which is somehow very modular, that you could split it into many, many different pieces, and different people will work on different pieces separately. But they would talk to each other, and there'd be some transfer that if someone made progress on one component of the project, that would help other people work on nearby components. It should be elementary. Otherwise, I would only get like 5, 6 people working on it. I wanted a very broad participation base, so the problem had to be not use too much sophisticated mathematics. It should be very diverse in ways you can approach the problem. So it shouldn't just be everyone doing the same thing. Some people might use computers. Some people might use algebra or group theory or whatever. There should be a different things you can try to attack the problem. And there should be a very clear goal. Ideally, one with a metric, like a number that has to go to 0. So that, in particular, if it's a very complicated project, if you can do any tiny contribution that sort of moves this number down by 1 or 2 towards the goal, you can actually see you can see that you've made partial progress. And it's not just a 0-1 thing of the project is complete or is incomplete. You have something that you can hill climb. And there should be some ability to visualize what you're doing. It shouldn't be so abstract that there is no good sort of eye candy way of seeing of measuring progress. So I thought this algebra problem would be suitable, and so about 6 months ago, sorry, I launched the project. I started by formalizing that tiny little graph, a 10 by 10 graph by hand with a little lean file, and the project was basically just to expand it to 4,000 other laws. Okay, yeah. So more precisely, we are studying magmas. Okay, so a magma is basically a group of no axioms. So it's a set M with a binary operation, and that's it. The binary operation does not have to be associative or has an inverse or anything. It just exists. Equivalently, it's an m by m multiplication table where the entries are themselves elements of m. Now, magmas can obey laws. So, for example, they could obey the commutative law or the associative law. We gave every law a number. So the commutative law is equation 43, the associative law is equation 4512, and so forth. It turns out that if you're only allowed to use the operation 4 times, there are 4,694 laws. And we say that one law implies another if every magma that obeys the first law obeys the second law. So this gives you some sort of directed graph between these 4,694 laws. Okay, so for example, the associative law does not imply the commutative law because you can write down a magma which is associative but not commutative. For example, any non-abelian group would work. On the other hand, here's another example. The left absorption law, E4, by substitution implies the law E10, x equals y times x times y times x. And in fact, every time you do have an implication, it must follow by a finite number of substitutions. Okay, so there are 4,000 odd laws. This generates about 22 million edges. And so basically, the project was to solve 22 million algebra problems. Now, most of these are easy. So you saw one example of where this method overflow user in 3 hours solved 1 or 2 of these implications. But that doesn't scale, okay? If it takes 1 hour to solve each implication, you cannot solve 22 million implications this way. These implications are not independent. They are related to each other. So, for example, you have transitivity. If equation n implies equation m, and equation m implies equation k, then of course equation n implies equation k. And there's also a duality relationship. You can replace a magma operation by its opposite, and that creates a reflection symmetry on this graph. So there are some relations. But the problem is hard. We do know that if you have enough, if the laws are complex enough, that the problem becomes undecidable. There exist pairs of equational laws where the question of whether one law implies another is actually undecidable. Related to that, sometimes if you want a counterexample to an implication, if you want to build a magma that obeys one law but not another, sometimes the counterexample has to be infinite. Now, we do have automated theorem provers like Vampire and C3, and they're very good at solving these problems. So a large fraction of these problems can be settled by existing software, but they're not guaranteed to terminate because of this undecidability. And so there's no tool that can handle 100% of these implications. Of these 4,000 laws, there were a small number that actually have some literature. So for example, here is a law, equation 453. It's called Tarski's axiom. It turns out that this law is satisfied precisely by subtraction. If you have an abelian group and this diamond operation is subtraction on the group, then it obeys this law. And conversely, if this law is obeyed, it must come from subtraction on an abelian group. So this is a very nice characterization of abelian groups, actually. But that's a very small minority of most of the 4,000 laws were basically have not studied before in the literature. So we have 22 million problems. There is no way that a single human or a single computer program can verify all of these. I think even Alpha Proof had a go at this and could only solve like 99% of these or something like that. So you need to collaborate. Also, if you want to combine it into one single statement, someone has to grade these 22 million problems. And that is also not capable, that's not something humans can do. So you definitely need the formal verification. So we were able to work out how to do this. So the project is completed. In 3 months, we completed, we settled all 22 million implications. So our workflow, this diagram is sort of to demonstrate, to illustrate what we did. So it has sort of 3 components. So on the left here, you have the GitHub repository. So this contains sort of the same type of stuff that you see in a formalization project. There's the formal lean proofs of all the various implications. There's a blueprint that describes a semi-formal description of many of these, but only a small fraction of it. The blueprint doesn't cover all 22 million implications, but it covers about 100 or so of the really interesting ones. but also some visualization tools to actually look at the graph and see what's missing, what we need to work on next, and what counterexamples we have, and so forth. Then we had our discussion. So we had the lean zulip, where people would supply proofs of individual implications, either generated by humans or generated by computers. And we would discuss them. We would try to deconstruct a human proof, and we would try to turn it into a computer proof, or take a computer proof and turn it into a human proof. And sometimes, based on that, we would either we try to formalize proof we already had, or try to write some software, either just ad hoc software in Python or Rust or something, or call one of the ATPs to start generating computer proofs, computer generated proofs. So there were basically proofs kept moving around this workflow in all kinds of directions. So it wasn't sort of a single linear cycle by any means. So for example, here are just some illustrations of things we did. Here is a human-generated proof by Bernard Ranke. He showed that he was studying a specific implication that whether equation 1648 implied 206, and he constructed a short counterexample to this implication. So that's a human-generated proof. Here is a computer-generated proof. Daniel Weber used an automated theorem proof of Z3 to show to find a counterexample to a specific implication coming from one. So the automated theorem prover created a specific multiplication table that was a counterexample. This is a more complicated story, and this screenshot is just like a small fraction of a long discussion. So a bunch of us had developed what we call a greedy algorithm, where if you want to build a counterexample, you can take an infinite multiplication table and just fill in the entries greedily to try to obey one law while also being a counterexample to another law. And you keep trying to fill in things greedily, but sometimes you get stuck. You find that the law that you are trying to satisfy also implies another law, which you have to make sure is also satisfied. And if you don't satisfy that law, your greedy algorithm can reach a dead end. So you have to keep adding more and more rules to your greedy algorithm until it converges. And we did this by hand for one or two specific implications, but then we realized that this process can be automated. And so there was a lengthy discussion how to actually automate this greedy rule set procedure. And then Daniel Weber actually coded up, I think in Rust, a search for all the to scan, all the outstanding implications to see which of them could be handled by this greedy method. We also have to convert computer proofs into human proofs. So just because a proof was proven by computer, it wasn't necessarily proven in lean, and so we needed to convert proofs, computer-generated proofs, into lean proofs. In fact, sometimes we had to convert lean proofs into lean proofs because we made a decision early on to have the core lean repository only use lean and no extensions of lean. This was for versioning reasons. It was hard to maintain all the updates to mathlib and so forth. We also had to update all the extensions, and also all the different collaborators, they would also have to update their extensions as well. But some collaborators did add on certain extensions like duper, and proved some of the implications using an extended form of lean. But then we had to convert that back to vanilla lean, if you wish. And in some cases, the way we did that was that we had humans deconstruct the formal proof back into an informal proof, like Amir did here, and then we would formalize that back into lean. Maybe there's a more automated way to do this, but this turned out to be more convenient in many cases. So basically, proofs got moved around from format to format in all kinds of directions. I mentioned before that Bernard gave a very short proof, a human proof that 1648 did not imply 206, and then another contributor, Shreyas in this case, by hand wrote down a lean proof, a lean formalization of that proof. So sometimes you could formalize by hand in a fairly straightforward way. Sometimes, so other co-authors would write code to automatically take, say, the output of a automatic theorem prover and convert it into a lean proof, just line by line translating the various steps of the ATP into lean proofs. In fact, I would say 95% of the proofs in the lean code base actually come from these sort of automated translations. We had, so yesterday we saw some talks about like some of the technical difficulties in formalizing, like how to get the definitions correct and to deal with universe issues and things like that. Magmas are quite elementary. Each algebra problem we had to solve, each of the 22 million algebra problems we had to solve, you can formalize in about 10 lines of lean without needing any without even needing mathlib actually. So we had relatively few issues of that form. Maybe I'll skip actually. They're not super interesting. We had a few minor issues, but nothing super interesting. I think I'll skip this slide. We used the GitHub issue system very much as Kevin described yesterday from his last theorem. So there'd be specific tasks that we would assign, like there'd be specific implications that we'd like to formalize, and then I or somebody else would give them as tasks, and then people would volunteer to claim them. Although one nice thing about this project is that actually it was actually a lot of it was decentralized. A lot of people just sort of spontaneously selected one segment of the graph to work on and just worked on it. I mean, we did use the issue tracking system for some portion of the formalization project, but people just understood the assignment and actually just there was a lot of spontaneous organization, which was great. I mean. With the polymath projects, which I worked on 10 years ago, a big bottleneck was having one moderator having to organize everything. And this actually stopped me from scaling. But one nice thing about a project as broad and so as modular as this is that you don't need 100% centralization. But there were some very complicated proofs, which the human proof were pages and pages long, and there we had to use the blueprint. But this is just one fragment of one blueprint of one application. But I would say only about 100 or so of the implications actually needed to use the blueprint. So the blueprint is actually only a very small portion of the whole project. We also developed a lot of nice visualization tools. Here is this is a graph. So there's a specific equation that turned out to be very annoying. The equation 854. It had a lot of consequences. It implied a lot of other laws, but it also seemed to create lots of counterexamples. And so to create counterexamples to magmas that obeyed this law but did not obey other laws, it was very tricky to create magmas that solved this equation, because this equation also implied all these other laws. And so any counterexample had to also obey a lot of other laws. And to navigate exactly what was true and what was false, it was very convenient to have some very nice visualization tools that many of contributors coded up. And this was also essential in allowing the project to decentralize. We also had some very nice dashboards. Like every day you could log in and just sort of see how far along we got with the project. So as I said, there were 22 million implications to prove. By day 16, we had formalized all but 888 of them. So a bunch were true, a bunch were false. We didn't formalize all 22 million statements in Lean itself. That would have taken forever to compile. We actually just formalized a smaller generating set of true and false implications, and then we use transitivity to then deduce the rest. And then there'll be a bunch of, on any given day, there will be a bunch of statements that were not yet formalized in Lean, but many of them did have informal proofs. So on this particular day, of the 888 non-formalized proofs, 107 implications, 174 of them were already known to be false, maybe by a human proof or maybe by an automated theorem prover. And then there were 10 that were consequences of these 174. And then there were still 704 for which we had no idea whether they were true or false. That was day 16. Right now, we have 0. Okay, so everything is formalized at this point. So this project kind of evolved in stages. There was this early, very, very hectic stage in the first 2 weeks where basically all. Sorry, is there a question?
We lost you just for a second, but you're back now.
Okay. Yeah, so for the first 2 weeks, we basically cleared out all the low-hanging fruit. So you can brute force using automatic theorem provers to try to solve these problems. You can test various small multiplication tables, such as all tables of order most 4 by brute force. You can test special laws, such as linear laws or translation invariant laws. And by trying all the cheap things, we could solve about 99.9% of all the problems. And there's basically 1,000 difficult ones that took most of the time. So then there's a second phase where we sort of identified the representative toy problems that the simplest unsolved problems that couldn't be solved by easy methods. We found one by one ways to solve each of these problems, and then every time we found a new technique, we tried to extend it and we applied it to as many of the other outstanding problems as possible. So, for example, there was this greedy method, which I already just discussed, which just tried to fill out an infinite greedy table. We first discovered it while trying to solve one particularly annoying implication, where the equation 65, which we nicknamed asterisks, implied equation 1491, which we nicknamed obelisks. Yeah, because we named it because these asterisks and obelisks are cartoon characters that resist the Romans for many, many years. Anyway, but we finally defeated them. And then that same method also settled hundreds of other implications by an automated search. We discovered some new mathematics. So we found new ways to use automatic theorem provers to make constructions. So initially, we just dumped the original implication into a theorem prover and asked, can you prove this theorem? But we found ways to sort of interactively use automated theorem provers where you make conjectures about intermediate statements that might be true, might be false. Use an automated theorem prover to quickly discard any conjectures that are obviously false, and use that to kind of narrow down what a counterexample might look like. So we could construct larger and larger finite counterexamples by this sort of guided approach. We invented a new type of cohomology. So group cohomology is the tool needed to construct group extensions. So we found that actually you don't need to have a group. You can actually construct extensions of a magma by some abelian group, and you need to study a magma cohomology group, which seems to be new. It wasn't known before. We also find that each law comes with a certain invariant, especially semigroup. It turns out that the variety of all magmas that obey a certain law has a certain invariance on it. It has a symmetry group. It's usually trivial, but there's a few laws which is non-trivial, and you can use that to settle some implications. And we found some automated ways to. Some laws have some special properties called confluence or having a complete rewriting system, which allows them to, you can settle all implications from a given law if you have this complete rewriting system. And we found ways to detect whether these things existed. As a spin-off, we also studied the finite version. Which laws imply other laws if we restrict the magma to be finite? And so that's a slightly different graph. And of the 22 million implications there, we could solve all but one of those implications. And it's dual. So we have one open problem from a whole project. And this is this specific, extremely annoying implication, which is an open problem. In fact, it's listed on the DeepMind open repository that was mentioned by Thomas yesterday. So one thing I want to close with is that we were hoping to also use machine learning and AI, but this was actually surprisingly disappointing. I think maybe if we had run the project today rather than a year ago, maybe it would be different. But we didn't actually find the modern AI, to be super useful. It was a little bit useful. The visualization tools that we built were basically built by Claude. The formalization, it was slightly accelerated by GitHub Copilot and things like that. there were one or two cases where, like, for example, we had to find a rewriting system for a certain equation, and I think O1 could actually correctly guess what the rewriting system could be after giving it some previous examples. But I think at the time the tools were not quite good enough to be super useful. Also, we were hoping that once we had completed a large portion of the implication graph, we could use machine learning to predict the rest of the graph. But actually, we had basically completed the graph too quickly for but by the time we had actually set up the machine learning and the neural network and run it, we had actually pretty much completed the whole graph. I think for more difficult problems, maybe machine learning could be useful here, but we didn't end up using it much. So what about the future? We chose a project that was sort of maximally favorable for collaboration. In particular, every single little proof was fairly easy to formalize in Lean. We didn't have this massive prerequisites such as in Kevin's FOT project. If you want to do something in a more advanced area of mathematics, for example, in analysis, if you want to combine lots and lots of estimates together, and they haven't all been proven yet, it's going to be a lot trickier. The bottleneck will be to formalize every single thing into Lean. For example, in PDE, many basic estimates inequalities in PDE, such as the sublevel embedding inequality, have not yet been formalized. So I think if you want to apply this paradigm to something more sophisticated, you have to do something. You have to first use an intermediate proof assistant between informal math and Lean, I think. I think what's going to be needed in practice is to actually create intermediate proof assistants that aren't as fussy as Lean. And so you don't have to spend all this time dealing with universe issues or whatever. You create some custom proof assistant that is tailored to your project. Your proofs are not completely verified, but they do impose some discipline on your informal proofs. And you train your AIs and your other computer tools to first write in this intermediate proof system, and then there'll be some sort of separate step to formalize, to transfer from this sort of weak proof system into something as reliable as Lean. I think that would be that would be a necessary ingredient if you want to replicate this later. But I think that's my final slide. So thank you very much for your attention.
Thank you. That was extremely interesting. I'm not sure how we should go about taking questions here. Maybe I'll just point at people. Is that the easiest? Yes. All right. Who'd like to go first? Yes.
Are there many cases of work which later became obsolete because it was implied implicitly by sensitivity? I could imagine that it's pretty off-putting for some contributors if you contributed something and later on it was just like an implication of some other work.
That certainly happened. I mean, there many implications that had multiple proofs. We didn't track. Well, okay. I think maybe what helped is that we just didn't track that. We tracked the aggregate statistics of how many implications were outstanding, and that was the score. So, like, if at the time you proved something, that made the number go down, and then if someone else reproved it by an automated search, that didn't change the number. But you were the first. You were the first to reduce that. But the same thing happens in informal mathematics too. Someone is the first person to prove something, and then someone else finds a simpler proof that reproves a lot of previous results, and that's progress. The aim of the game is not necessarily to be the last person to own a certain implication. So yeah, we didn't attach. We didn't sort of try to attach specific people's names to specific implications.
Yeah, and I wanted to ask about the participants, because in the earlier slides you were talking about citizen science and the general public being able to take part. Were the people that were taking part mostly professional mathematicians, or who was?
Only very few, actually. I think I would say only about like a quarter were professional mathematicians. Well, at least like um, um, uh, well, there were some graduate students for sure. There were some undergraduates. A lot of people from computer science contributed, especially people who were good at the automated theorem provers. And there were people who I think were just members of the general public who liked solving logic puzzles. Um, and there are people who liked Lee. Uh, I didn't track actually the demographics. Uh, Somewhere in our paper, we are writing a paper right now, and people have to contribute their affiliation, and there's a fair fraction are unaffiliated. Um, yeah, so it is this project I think does have a much broader participation than a typical math research project where you basically need a math PhD to maybe even understand the project that you're trying to work on. Here we deliberately chose a project which you basically need an undergraduate level algebra education to understand, and which is still a little bit of a bar, but a lot less than many other math projects.
So the neural networks were useless. You already did it before, but could you use that in retrospect to see would it have helped? I mean, with all the stuff you have now, you could see whether that would it have helped to discover some of these things. And also, I don't understand. I mean, the neural network would it just predict whether the implication is true or not, or does it actually give a proof?
Right. Yeah. So the way we use them, we just use them to predict the graph. So we fed the neural network like 90% of the graph, and we asked, can you predict the last? Oops, can you predict the last 10%? And it could do so with about 80, 90%, or maybe I forget the exact numbers, but with fairly high accuracy. Although it could be that it was just learning transitivity and other basic properties of the graph. One thing we found was that well, by the time we were doing this, we conjectured that all the implications that were still outstanding were false, because it turned out that every time an implication turned out to be true, an automated theorem prover could actually prove it really, really quickly. So all the positive implications were actually quite short, like 10 line proofs. Well, there were a few that were 100 lines, but these ATPs have been developed for 20, 30 years. They've become very, very good at these sort of things. But all the negative proofs were usually quite long. Occasionally, an ATP, maybe about half the time or something, could settle a negative implication by constructing by brute force a counterexample. But usually, you need to construct counterexamples that are quite large, maybe at least 5 elements or infinite. And ATPs were not very good at that. So by the time we were trying this machine learning algorithms, we had already, our strong belief was that we had already found all the positive implications. So it wouldn't have helped us for this particular problem. If there were a future project where both positive results and negative results were equally challenging to prove, then I think machine learning would be more helpful to sort of to give us good guesses.
And is there any correspondence table of these obtained results with the human mathematical results? For example, I see that there is maybe possible to have correspondence with standard group theory, Lie algebra theory, various geometries.
Right.
Yeah.
So there were several people who independently, just spontaneously decided to formalize some existing results in this area. So this area is called universal algebra. So I mean, as I said, individual equations have been studied, and there were people who sort of did side projects within this broad project where they formalized some additional facts about specific laws, which occasionally actually helped us with the project. For example, there's one law that formalizes that formalizes a Boolean algebra, and Boolean algebra is a complete theory. We know exactly what laws are true for Boolean algebras and which ones are not. So someone verified that this law described a Boolean algebra, verified and then he could settle all the implications from that particular law. And so that helped our project. But yeah, so people actually did all these spin-offs spontaneously because we had this platform, um, and they could use the implications that were already proven, or some of our basic API and so forth. Yeah, so people did sort of merge things a little bit with the literature.
Thank you.
Can you comment on the difference between the full implication graph and the one for finite magmas? So, and how big is the difference, and is there interesting structure to it?
Yeah, so there's only about 1,000 odd edges which are different. Yeah, so the thing about finite sets, mostly what happens is that sometimes there are laws that imply that a certain operation is injective, but not that it's surjective. But on a finite set, if you take a map from a finite set to itself and it's injective, then it's automatically also surjective. So this is sort of extra axiom that injectivity and surjectivity are equivalent in the finite case. And that already explains most of the discrepancy, that there these extra positive implications that you can get just by using the axiom. So in fact, most of those, what we did was that we just basically gave Duper the axiom that injectivity and surjectivity are equivalent. And with that, Duper was able to settle a lot of the outstanding implications. But there were a few more weird ones that required some ad hoc proofs. Yeah, so there's about 4 or 5 that had some clever proofs. You had to use like the cycle decomposition for permutations, that every permutation on a finite set splits up into a finite number of cycles. That was used in one proof. And I forget, there was a couple other things like that. The one hard thing was that our most powerful counterexample technique was the greedy method, this greedy algorithm. But the greedy algorithm only created infinite magmas, and so we had to, in order to complete the finite graph, we had to construct many more finite constructions than we had before, and that was very ad hoc. We used ATPs, we used lots of conjectures, and we used we developed magma cohomology, in fact, precisely to do that. Yeah, it's just like, you know, to construct finite groups, there are lots of clever tricks to construct finite groups. We had to construct lots of interesting new methods to create finite magmas that obey specific properties.
Having done that, how many implications are left for which the greedy method is required?
This is I can't answer that question accurately because for each method, we only applied it pretty much to the implications that were outstanding at the time. I think by the time the greedy method was developed, there were only about 1,000 equations outstanding, and it settled about 300 of those. We did not apply it to the entire 22 million implications. We could maybe, but yeah, so we have a very distorted view of which tools were the most effective. So, for example, ATPs, so like about 95% of our implications were solved by ATPs. But that was partly because someone coded that up very early in the project, whereas some of the other techniques took a lot longer. If these tools were done in a different order, then the percentages of completion rates would be very different.
Thank you. Yes?
I have a question about magma cohomology. Do you think that would be an interesting theory in its own right, say for standard papers, that should it be useful to add to math it?
I don't know. Well, okay. What it allows you to do is it allows for a very general way to construct new magmas that obey specific laws. So within universal algebra, which is the study of laws of various operations, the same technique, you know, you could apply it for similar problems. If you want to know whether one random-looking law implies another random-looking law, for maybe if you have multiple operations, not just one binary operation, but several, you could try to construct similar things. Outside of universal algebra, I don't know if there would be an implication. We asked some category theorists. They had not seen this particular type of construction before. It's not a full cohomology, by the way. It only goes as far as H2. There's no H3, H4. There's no higher cohomology as far as we know. That seems to be specific to groups. Yeah, but I don't know actually. But lots of discoveries you don't have an application for initially. So who knows?
Maybe one more question. Yep.
How feasible would it be to create a website with a really nice interface? So if anybody in the future had a sort of Math Overflow style question along these lines, they could just go to that website, type in the rules, and either get a nice sort of humanly readable proof that one implies the other, or humanly readable example that shows that it doesn't.
Well, we have a tool. I mean, for a specific, I mean, I might even be able to share it, actually. Let's see, if I have time. So if I, let's see. So can you see this webpage? So the tool we have is called Equation Explorer. So you can take any one of our equations. For example, let's take the commutative law 43, and yeah, it shows you all the equations that are implied by this law, which ones are not, and like if this one is not implied, somewhere there's a proof. Okay, and here is the here are the two lean lemmas, which demonstrate that this law does not imply this law. And then I think you can click on those, and then you can actually see the actual lean proof if you want. So we do have some interfaces specifically for this project. I'm not sure you're asking for a more general thing where you take actually arbitrary statements, and it. I mean,
I was wondering how easy it would be to convert something like that into something that somebody who knew no lean could understand, but that might be rather.
I mean, it should be doable. I mean, all the data is there. You just need somebody to build an interface. But I think with modern AI tools, you could whip up something if you wanted to. Yeah, this was good enough for our purposes. We didn't develop it further.
Okay, well, I think we should, oh, well, you want to squeeze in one more question? We have 2.5 minutes.
Make one comment that when we give our last round of applause to Terry, let's keep in mind that it's 2 a.m. in California.
Oh, yes.
So we are very grateful for this heroic effort.
You're right, I didn't do the calculation. Yes, that's, it doesn't look like it's 2 a.m. Good work. You look very enthusiastic and very alive.
Yeah, it's completely black outside. Yeah.
Thank you very much. It was an extremely interesting talk.